4-2 degrees and radians. So first we're going to talk a little bit about angles in standard position. So your initial side of your angle is a fixed ray. That's where the angle starts. Let's go ahead and write starts here. So an angle is going to be two rays, which kind of makes sense if you think about an angle shape. You have two rays for that. So your initial side is the fixed ray. That's where your angle starts. And then terminal is going to be the ray that's rotated around our vertex. That's going to be where the angle ends. So it starts at your initial side and it ends at your terminal side. So for example, an angle in standard position will have an initial side over here at your x-axis, and then the angle itself will rotate, let's say counterclockwise around the vertex, which is the origin. And then this would be my terminal side. So I've got my initial side, I've got my terminal side, and my ray is being rotated around that vertex, which is the origin, and that means I'm in standard position. So this is standard position for an angle. If I am looking at an angle like I just drew that's counterclockwise, it's going to be positive. And then if I have an angle that starts over at the x-axis, let's do a different color. So let's have an angle that starts at that positive x-axis again, but rotates the other way. That is going to be a negative angle. So clockwise is going to be negative, and counterclockwise is positive. So the way we are going to draw our angles is like this. We're going to start on the positive x-axis, and then we're going to rotate them around either counterclockwise or clockwise to our terminal ray, and that's going to be how we draw those angles. We're going to be rotating them around the origin. So first we're going to go through and practice drawing angles a little bit. So we're doing a little bit more than what your textbook has. Normally example one that I do is going to correlate with example one from the textbook, but not for this section. We're trying to go through and kind of fill in gaps that you might have from knowledge last year. So if we want to draw 135 degrees, let's think about how 0 degrees is right here. 90 would be right here. This is going to be 180. All the way around is 360, and then this negative y-axis would be 270. So if I am going to draw 135 degrees, 135 is between 90 and 180. So my angle is going to start here and go around and stop. And then I'll just draw that terminal ray. So because it is understood if I'm drawing in standard position that I'm starting at positive x, I don't even have to draw that in. I don't have to draw that initial ray. I only have to draw where the angle ends. And then I do like to draw that little arrow around to kind of show the direction that you're rotating in. So 640 I know is bigger than 360. So I need to do 640 minus 360 to figure out exactly what's going on there, and I get 280 degrees. So that means that it's 360 plus 280, so it's all the way around, plus another 280 degrees, right? Because all the way around this entire coordinate plane would be the 360, and then it's plus another 280. So the way I show this is I would show all the way around, and then another 280, and we know 280 would be just past 270, so I would draw it like this. So I'm drawing something that shows all the way around one time, and then back around to the 280. So that's how I would draw this, and I'm going to label it 640 degrees. I did not label the last one, so let's go ahead and label that. The next one is a negative angle, so now I'm going to start at that positive x-axis, but I'm going the other direction, and so I need to think about how this is 0, and if I'm moving in the negative direction, this is negative 90, this is negative 180, and this is negative 270, and this is negative 360. So negative 105 would be over here, just past negative 90. And then again, I do not need to draw my initial side, just my terminal side on that angle. So just a little bit of background on drawing angles that you might have missed last year. This is kind of a combination of Algebra 2 and Precalc stuff. So coterminal angles, when two terminal sides coincide, and they're found by adding or subtracting multiples of 360. So that means on the last example, just as a little note. That middle one, 640, was coterminal with 280 because those ended in the same spot. One of them went all the way around and stopped at the 180 and then, or sorry, at 280, the other one would have just gone to 280, but those are coterminal. So just, we've already kind of had a little bit experience with that then, and we can get them again by adding or subtracting multiples of 360. So for example, we want to find one positive angle and one negative angle that are coterminal. So to get a positive angle, normally we're going to be adding multiples of 360. To find a negative angle, normally we're going to be subtracting multiples of 360. So if I have negative 215 and I want to find a positive angle, I'm going to add a full revolution, which is 360. And then I get 145. So that gives me 145 degrees is my one positive angle. And then if I want a negative angle, I am going to subtract 360 degrees, which is negative 575 degrees. So there we go. On the next one, to find a positive, I could add 360. And there's going to be a lot of different answers on this because I could just keep adding 360s and get more answers. So 930 degrees would be one answer. And then if I wanted a negative coterminal angle, I could take 570 and subtract 360 degrees. But I can tell that when I subtract 360, it's still going to be positive. So that could be also an answer for my one positive angle. So I'm going to have to subtract 360 one more time because I want to have a negative coterminal angle. And if 570 minus 360 is still positive, then I have to subtract it again. And that would give me a negative 150 degree angle. So those would all be, these two would be coterminal with 570. The negative 575 degrees and 145 degrees are coterminal with negative 215. So this is something from your textbook. It is not really going to be a huge deal this year, but I think it's worth us just briefly going over. We're going to take each decimal degree, and it's in DMS. DMS stands for degrees, minutes, seconds form, and we're going to convert it to a decimal instead, or vice versa. So let's see, degrees, minutes, seconds. So basically what they do is they take a degree and they subdivide it into 60 minutes. And I'm trying to figure out where we should put this, maybe at the bottom. So let's write a little note here. Each degree is subdivided. And this is in our quest for fractions, right? Because we don't like decimals. So each degree is subdivided into 60 minutes. And we write it like this, 60, and then one little slash, that means minutes. And then each minute is subdivided into 60 seconds. And so 60 seconds would be like a little double slash there. So minutes is 1 and 60 is 2, and seconds is 2. So let's kind of get a feel for how to do this. Again, this is not a super big thing for what we're doing this year. So this means I could write this as 329 degrees plus 0.125 degrees. And I know that in 1 degree, there's 60 minutes. So I'm going to multiply this by 60 minutes per 1 degree. And then let's see, that's going to be 329 degrees plus, when I have degrees on the top and bottom, they cancel. 0.125 times 60 is 7.5. And again, because the degrees canceled, it was top and bottom. When I do 0.125 times 60, I get the 7.5. And now I am left with minutes. And I want to keep the same color here. So now I have the 7 as a whole, so I'm happy with that. 329 degrees plus 7 minutes plus, the problem is I don't want to have decimals, so 0.5 minutes. So now I know that In 1 minute, there's 60 seconds, so 60 seconds per 1 minute. And now I have minutes, so that minutes will drop out of there. And when I do 0.5 times 60, I have 30. And that's going to be 30 seconds. And then to write that, I would just write, maybe we'll do our final answer in blue here, 329 degrees, 7 minutes, 30 seconds. So again, this is just in our quest basically to not have decimals. So by taking anything that's a decimal and we like further divide degrees, further divide those minutes, it lets us just not have any decimals at all. So we just have lots of fractions, which math people like. So on the next one, we're starting out with degrees, minutes, seconds. We want to convert it to decimals instead. So 35 degrees. And then if they have 12 minutes and 7 seconds, I'm going to convert those. So the minutes, I'm going to use that conversion the other way around now. In 1 degree, there are 60 minutes. And then I have 7 seconds. So I know that for 1 degree, there is 60 minutes, and each minute is 60 more seconds. 60 times 60 would be 3,600 seconds. And then again, top and bottom, I've got minutes or seconds, so those are going to cancel out. And so now we're going to get a bunch of decimals back. So 35 degrees plus 12 divided by 60, that's going to be 0.2, and I'm left with degrees plus, and then I'd have 7 divided by 3,600, which is 0.0019444 degrees. So this is 35 point, and then we're going to put these decimal parts together, 2019444 degrees, and then it tells us nearest thousand. So I'm just going to write in here nearest thousandth. I'm not really enunciating that well, so nearest thousandth, which means this is a tenths, hundredths, thousandths. So 201 would round up, and I'd have 35.202 degrees. Again, this is just a really small part of what we're doing. You're not even going to be tested on it later on, but it's just kind of working with units and fractions and degrees and getting a feel for how this works. So radians, however, are very important. So 1 radian is the measure of an angle in standard position whose terminal side intercepts an arc of length r. Because c equals 2 pi r and r is 1, there are 2 pi radians. So on the unit circle, our r is 1, and then we just end up with 2 pi times 1. So we have 2 pi radians. That means if a whole circle, the circumference of an entire circle is then 2 pi radians, and 360 degrees would be a whole circle. So we get this conversion that 360, this is really the important part, equals 2 pi radians, or 180 degrees equals pi radians. And degrees, we have to have that degree symbol, but for radians, we just kind of assume if you don't have degrees, it's radians, just so you know. And so if we are already in degrees, we want to cancel them out, we would multiply by pi over 180. If we're starting in radians and we want to go to degrees, we want to cancel those radians out, we'd multiply by 180 over pi. So I don't know that you really need to write all this down, because I think it's going to just make sense if, remember, units on the top and bottom are going to cancel. And that's really what we're looking to do. So basically what we need to know is that one circle, 2 pi is equal to 360, and pi is equal to 180. So for example 4, we are going to go ahead and practice converting. I want to convert to radians. So if I have 75 degrees right now, I know that my conversion factor is that pi radians equals 180 degrees. So I'm going to make that a fraction. And I want degrees to cancel, so I'm going to have 180 degrees in the denominator, and I'll have pi in the numerator. So no degree symbol means our answer is in radians. And for degrees, we must use degree symbol. If you do not use a degree symbol, I'm going to be taking off points because I'm going to assume your answer is in radians. must use degree symbol. So I'm going to multiply 75 times pi over 180, which is just 75 pi over 180. We had degrees on top and bottom, so those are gone. They have canceled. Then we need to reduce. So if I divide both by 5, it looks like I have 15 pi over 36, but I can still keep dividing by 3. And then I would have 5 pi over 12. So this would be my answer in radians. So radians do not have to have a pi symbol in them, but they often will. The next one, I start out with negative 5/4 pi or negative 5 pi over 4. Again, we're trying to cancel out radians this time, so I'm going to want to cancel pi. Pi will go in my denominator, 180 degrees in my numerator. So now pi is gone. Let's see, 180 divided by 4 would be 45. Negative 5 times 45 degrees now. Let's see, that's going to be negative 225 degrees. So if you are using degrees, make sure you have a degree symbol. So this is just, we need to develop a sense of how radians and fractions work. We need to develop a sense about how radians and fractions work. So that's why I have this page up. So we're just going to draw a little bit and think about this. So if I'm looking at, I kind of think I want to look at this maybe a little bit. If I am thinking about just this unit circle, and I'm thinking about 0 degrees and 90 degrees and 180 degrees and 270 degrees, and I want to convert this to radians, I know that 0 would just be 0. I know that all the way around, and so let's see, all the way around would be 360 degrees. I know that's the same thing as 2 pi. I know that 180 is the same as pi radians. So if I'm thinking about 90, 90 is halfway between 0 and pi. So this is going to be pi over 2. And if I want to think about 270, 270 is halfway between pi, between 1 pi and 2 pi. That's going to be 1.5 pi, which is 3 pi over 2. So by thinking about fractions, you know, if this is a pi, then this is half pi, this is 1.5 pi, this is 2 pi. I can kind of quickly convert between the two just by using some common sense. So let's remember that all the way around a circle is 2 pi. Let's remember that half a circle is just pi. Let's see, we did the pi over 2 and 3 pi over 2. So let's now use some common sense about 30 degrees. So 30 degrees is going to be 1/6 of 180, right? 1/6 times 180 is 30. So that means when I go to draw 30 degrees, it would be pi over 6, because it is 1/6 of 180. So if I look at multiples of pi over 6, I'm looking at multiples of 30. So if I have 5 pi over 6, I would have 5 times 30. If I'm thinking about 60 degrees, 60 degrees is 1/3 of 180 degrees. And so if I want to think about 60 degrees, and I'm always going to start them at this positive x, that would be something like this, and it would be pi over 3, because it is 1/3 of 180 degrees. So 60 would be pi over 3. So if I have multiples of 60, I have multiples of pi over 3. So if I have like 7 pi over 3, then I would have 7 times 60 degrees. If I am looking at 45s, because special triangles, right, 30, 60, 90, 45, 45, 90, those are the important ones. 45 degrees is 1/4 of 180 degrees. So if I want to think about a fourth of then pi, so let's see, this is half pi. So a fourth pi would be like this. So let's label this one pi over 2. This would be pi over 4. would be this right here, and that would be the same thing as 45 degrees. So if I have multiples of pi over 4, I'm looking at multiples of 45. Let's draw all these little arrows in to show our angle rotating from that standard position where x is positive. So this is just to kind of help you make some sense of angles. A sector is a region of a circle bounded by two radii and an arc of a circle. So for example, here's a radii, here's a radii. This could be a sector. The central angle of a sector is the angle formed by the two radii. So this would be that central angle in that case. So the sector is a whole region, and the central angle is just around the center of that circle where your two radii are formed. So here are a couple formulas. If I want to know arc length, so this would be, when we talk about arc length, we're talking about how long this is. It's a portion of that circumference. And we would get the arc length, and arc length, the letter for that is S. We do R times theta, but this is when theta is in radians. And my area almost looks kind of familiar. We think of like 1/2 pi r squared, but this is 1/2 r squared theta when theta is in radians. And again, when theta is in radians, there's a pi in there. So it's kind of interesting. And so this is whole area of that entire sector. So that's on that previous page when we looked at sector, that's what we were talking about. Now we're talking about finding the area of that. And again, has to be in radians. So let's do sector is your, let's write down it's your shaded region. This is our arc length. I went ahead and did in red, so I'm going to kind of move over and do a better arrow pointing to that. And then just to keep labeling, theta is the central angle. And again, it's in radians. Has to be in radians or the formulas do not work. So you might have to convert before you can do anything else. So now we're going to look at an example on this. If I want to find the arc length and area of a sector, and I have r equals 6 and theta equals 50 degrees, they both require theta to be in radians. So first thing I have to do is convert. So first we're going to convert. So my theta is going to equal 50 degrees times, my conversion is that 180 degrees equals pi. So I'm going to multiply by pi over 180 degrees. I want the degrees to be on the bottom, so it's top and bottom and they cancel. And let's see, I could also divide out those zeros basically. So because I can divide them both by 10, I would have 5 pi over 18. Now that I have my theta correct, to find my arc length, and my arc length is S. I know that S equals R times theta, and so my R is 6, and theta in radians is 5 pi over 18, and then I would want to simplify that. So let's put 6 over 1. 6 goes into 18 3 times. So my sector, or my arc length, which is S, not at all confusing, right, is going to be 5 pi over 3. So that's the length of my arc. And then for the area of my sector, I'm going to use the letter A. And that formula is 1/2 r squared theta. And this is for area of a sector. I'm sorry, these notes are really long. There's just a lot of information today. And so A equals 1/2. My radius in the original problem again is 6. So 6 squared. And then times theta, and theta is 5 pi over 18. It's that angle in radians again. So let's see, this is 1/2 times 36 over 1 times 5 pi over 18. So I'm pretty sure 36 divided by 2 is 18, but then there's also an 18 here. So we just end up with an area of 5 pi. So our area is 5 pi units squared, and our length of the arc there, my arc length is 5 pi over 3. So last example, and we're just kind of barfing a bunch of information on you today. I am going to make a note here at the top, which means I'm going to have to move all these problems down. And this is stuff that we will be spending a lot of time on actually tomorrow and the next couple days, but we need to memorize. If we're going to work with all these crazy angles, like 150 degrees, 315 degrees, that are on that coordinate plane, that means I don't have a triangle in space anymore. When I have them on a coordinate plane, I need to memorize my trig functions a different way. So on my coordinate plane, I am going to say that the sine of theta is equal to, instead of opposite over hypotenuse, we're going to do y over r. My cosine of theta is going to be x over r. My tangent of theta is going to be y over x. And then I've got all those reciprocal functions, cosecant theta, r over y. Secant of theta is r over x. And cotangent of theta equals x over y. So let's take a look at why we even care to do it this way. So my sine is, again, y over r. 150 degrees means I am going past, I'm starting at positive x, I'm going past the 90, 150 is going to be over here somewhere. This is going to be 150 degrees. And then in order to make this somehow into a triangle, I'm going to draw a perpendicular to the x-axis. So that means from here I'm going to go down to my x-axis and make an angle. And then this is actually going to be a special triangle. If I think about how all the way to this line, to my negative x-axis is 180, and then this ray right here is at 150, I have a 30-degree angle in between them, which means I have a 30, 60, 90 triangle, which means my sides on my triangle, this vertical side over here across from the 30 would be 1. My hypotenuse would be a 2. And the side across from the 60 would be the square root of 3. And because it is on my negative x-axis, this is going to be negative square root of 3. So now you can see if I'm looking at doing the sine of 150, I can now just look at this triangle here and have this as my central angle that I'm working with. And so instead of having opposite over hypotenuse, it's going to be easier to work with this as my y side over my r side. So remember, when we look at a coordinate plane, y is going to be up and down. So y is going to be your vertical side. X is going to be your x-axis. It's going to be your horizontal side. So we'll have our x side, our y side, and our r is always going to be like the hypotenuse on there. So when I find my sine here, my sine of 150 degrees is going to be my y over r, which is going to be 1/2. So this is really the heart of what we want to be able to do. There's a lot of weird stuff in 4-2. Even though this is not really in your book, I wanted to go through this now because it's the important part. And we're just kind of barely touching on that today. So cosine of 315, I need to first draw that one. So here's 0, past 90, past 180, past 270. 315 would be in here somewhere. And I always want to draw my triangle by connecting a perpendicular to my x-axis. So here's my x-axis. I want to connect there. We never connect to y. If this is 35 and this is 360, between those two would be a 45-degree angle in my triangle. So it's a 45, 45, 90, which means 1, 1, square root of 2. And because this vertical side is down, it'll be a negative. So I have my x and my y and my r sides. Maybe we should label the other one, x, y, r. If I am looking for cosine, I'm looking for x over r. And so my cosine of 315 degrees equals my x side is 1, and my r side is square root of 2. And then we need to rationalize by multiplying by square root of 2 over square root of 2. So the cosine of 315 degrees would be square root of 2 over 2. Last one, tangent of 5 pi over 6. So I told you that pi over 6 was equal to 30 degrees because 30 is 1/6 of pi. So 6 pi over 6 would be 180. This is going to be really close to 180. So let's go ahead and draw it over to here. 5 pi over 6. So inside, draw your triangle down to the x-axis. The line would be pi or 6 pi over 6. So between the 5 pi over 6 and 6 pi over 6 is just a pi over 6 inside, which is really 30 degrees. So across from 30 is a 1. My radius, or my hypotenuse side, is 2. The other one is square root of 3, but it would be negative again. So this is really a repeat of what we did for that first one. And then to find my tangent is y over x. So tangent is like slope, y over x is slope. So let's go ahead and label this. My y side is vertical, my x side is horizontal, my r side is that hypotenuse. So the r is never going to be negative. So if I want to take the tangent of 5 pi over 6, I would have y over x, which is 1 over the negative square root of 3. And then we would need to rationalize by multiplying by root 3 over root 3. And so my tangent of 5 pi over 6 is going to equal the square root of 3. I guess the negative, I don't really want my negative with my denominator, I want it out level here. Negative square root of 3 over 3, because I had to rationalize that. This was a lot of information, a lot of notes today. Hopefully that beginning stuff seemed kind of easy. It's mostly vocabulary heavy. And like I said, the stuff at the end, it's a lot of information today. So tomorrow we're going to start kind of tightening up our focus on what is important in this chapter.